So here we have an interactive application which one of my students developed a couple of years ago to illustrate this problem. Now, so what he's doing is interactively outlining the major boundaries of the quadrilaterals that project from the rectangles that conform to this 3D orthogonal system. And what he'll do in this demonstration is simply to show that if you have these facets of these buildings, then in principle one can construct a correct three-dimensional model from that information. You do not have the scaling factor for the model, so you don't know if it's a dollhouse or a complete full-scale model. Now, he's doing this interactively, and I can't actually show you. I just got a 5-minute sign for Richard, so I'm going to quit this and show you. Rather fast forward to the automatics section. So what I was supposed to show you there was how interactively, once you do this, you can then create this three-dimensional model. The problem, of course, is that that's an interactive process, and we can't afford to do that interactively for every camera view in the world. So the problem is, how do we automate that process? And so I've been working on this in preparation for this project. We have a ground truth database at York which we developed for this purpose. What I'll do is just skip ahead to some of our results on this problem. So what we've managed to show is we've developed a method that is roughly twice as accurate as previous methods, and about 5 times faster. So currently this is able to recover the camera parameters in roughly 5 seconds on standard hardware. So this is not real time, but it doesn't have to be. This part of the project is to establish a three-dimensional correspondence between the camera and the scene. So what's important is that it operates at a time scale that's smaller than the frequency with which, or the time between changes in pan, tilt, and zoom. So that's a reasonable amount of time. This shows some 2D examples of this estimation process. Okay, I want to speed ahead a little bit because I've got 2 more components I want to quickly touch base on. The third is what I call the problem of attentive cameras. So in addition to, so once we've, let's say, oriented the camera in 3D, we have a problem of actually extracting the interesting dynamics. And one of the things we've been interested in is how we can build better cameras in order to do that. So this is an example of such a camera we call an attentive sensor, which has 2 components. It has what we call the pre-attentive sensor, which provides a large field view of an environment. And then it has what we call the attentive sensor, which provides more detailed information of a very restricted field of view. And the key thing is that that is the attentive sensor, which is on a pan-tilt platform, which moves around. So so this is a valuable system in the sense that it can provide human-like capability. In human vision, we have a large field of view, but we have a fovea, which allows us to look around and get detailed information. The question is, where would we like such an attentive sensor to look? And ideally, we might want to model human attention, which is a very complex thing. In this project, we focused more on being able to find and fixate on people in the scene. And to do this, we use a set of fairly weak statistical cues, which, when combined, provide a fairly strong inference. To show you an example, here's the cue of motion on a particular image, the cue of background subtraction, the cue of skin color. Each of these is fairly weak, but when combined, statistically, they provide a much more focused set of hypotheses of where people are in the scene. And this just shows a quick qualitative video of the system performing and fixating on people and then verifying the presence of a person and saccading to another person. So I think this is a second component that we need to work on, which is the ability to extract, to detect where the interesting dynamics are, and be able to selectively record those. Serious problem. And one of the things this provides us with is with a relatively low-cost sensor to be able to extract fairly high-quality data on facial appearance. Okay, so the very last topic I'll just briefly mention is traffic analysis. This is probably the least developed part of the project, but I think it's possibly one that will come to fruition more quickly in terms of commercial ability. So monitoring traffic in a large urban environment is obviously a very important problem. One of the key ways it's done is through inductive loops. However, these are costly to install, costly to maintain. In many cities like Toronto, though, we also have video data for highways. The problem is we're back to the kind of user interface problem. This is typically the way these data are processed. We have individuals looking at very large banks of monitors. So we're motivated to understand how we can use computer vision to hopefully use these video data to extract useful analytics on traffic flow. So I think we are fortunate in Toronto in having one of the world's most sophisticated networks. We have cameras on all the 400 highways in the GTA, located at 1 kilometer spacing. They're generally pan-tilt zoom units. And these are all digitized and communicated over IP to central office. You can, many of you have, I'm sure, access these data through the Compass web system. And through that system, you can get updates, video updates every 3 to 5 minutes. But of course, the actual data are much higher quality. So this is an example of the data that's actually available. Actually available over IP at MTO. So the quality of the data is actually quite high. Okay, so our goal then is to be able to use these data to extract traffic information. The first thing we need to do, as for the urban modeling problem, is to be able to determine the pose of the pan-tilt camera relative to the highway. So that's the problem we're working on now. It would be tempting to try to use the classic linear perspective cue. The problem, of course, is that highways aren't always as cooperative in being perfectly linear structures. We have curves in highways. And so the problem with the approach we are taking is to do it in a much more general way. That is, to be able to detect those little dashed lane marks on our highways, to be able to group them, and then recover curvilinear lane structures. So this is the first stage in being able to recover the geometry of the highways and then be able to rectify them to metrically track the traffic. So just in the next couple of slides, I'll just show you the work we're doing on this problem. So this will be like a collage of images, just to give you a sense. So the first stage is sort of a match filtering stage of trying to detect these lane marks. Of course, we get many more hypotheses than we can handle. But this is first in stage 2, reduced to only those lane marks that have that are more probably lane marks than background. In stage 3, there's a further constraint, which makes use of the fact that these marks have to be a certain distance apart. So we're applying constraints of the problem that can be used to weed out impossible hypotheses. There's a refinement stage, then there's the problem of actually figuring out how these marks get grouped into separate lanes. So we start with a very dense association graph. We apply a set of sort of classical Gestalt grouping cues, determine the statistics of these cues, and these can be used to form a sparse association graph where the likelihood ratios are again more than 0. This is further reduced to something called a bipartite subgraph, which then admits an exact solution using, for example, a Hungarian algorithm to yield a maximum probability matching. Now, this is where we're at with this project. The goal is then to be able to use this information to recover the rectification. I want to point out that this is not a perfect result, but we haven't yet exploited the most powerful cues that are available here, such as the fact that these lanes are always parallel and they're actually of fixed width. So what I think is true is that these imperfect results actually are indicative that the problem is solvable. And so I think that we have an opportunity here to actually do something useful for administrative transportation. Okay, so I think I've used up my time, so let me just go to, let me try to go to my conclusion slide. Okay, so the moral of the talk is supposed to be that we have two problems. We have the problem of trying to bring these 3D urban models to life, dynamics. But I'm claiming there's a dual problem, which is that we would like to take all this 2D video infrastructure and put it in proper context to make it actually possible to infer what's going on. And I see these as dual problems, they're really different facets of the same problem. And I think it's a very appropriate problem for us to be working on as a community. I think there are many possible applications. Obviously, it's a very ambitious goal. The solution's not going to come at once, but I think that solutions to sub-problems are very likely to lead to more specific technologies. So an example would be, for example, highway surveillance. Okay.